Okay, let's get started. Morning, and welcome to the first formal lecture of nanomanufacturing. Today's topic is the taxonomy, or naming, and geometry, things about crystal structures and placement of atoms of nanostructures. One of the topics that we'll certainly build upon, and I think is important foundational knowledge for the types of structures we're going to consider, properties and processes as the semester moves on. And I'll always start the lecture with some announcements. So first, can I have a show of hands of people who are here for the first time, who weren't here last week? Okay, so please take one of these information sheets and just fill it out and give it to me after the lecture finishes. This is just for my personal knowledge of your background and your interests, and I'm going to take a look at all of these and get a sense of where you all are from and why you're taking the class. Also, if you had asked me last time about seeking an override, we've increased the enrollment limit. It was before 40 and now it's 60, so you shouldn't have any problems registering. You may need to, I don't know really how it works, you may need to drop it and then take it again, but as far as I know it should be okay. And also, if you're not on the CTools site for some reason, tell me and I can add you manually. Just send me an email. I wanted to say a couple words about prerequisites and grading of the class. A few of you have asked by email because of your different backgrounds or that you're undergraduates. About, say, not having taken the courses that I said in the syllabus are prerequisites for this class. So basically what I think is there's a set of knowledge that is, I could say, associated more so with mechanical engineering as a department than any other department or field that we're going to build upon in the class. And this includes topics in basic solid mechanics and fluid mechanics and heat transfer. Things like cantilever beam bending and pipe flow and conduction of heat. But if you haven't been exposed to those topics, or if you maybe have had similar topics, but not all of them in chemical engineering or material science, I think you'll still be totally fine, but you might have to do a bit of background reading to get up to speed. I'm going to do my best to let you know what I believe those topics are. I can't cover them in full detail as part of our lectures, and hopefully if you have further questions, I can guide you to background material. In practice, in terms of doing homework assignments, I want to encourage you to work together, although I want to strictly say that the homework solutions you submit should be prepared individually. That means that I want you to break away from the group to actually write up the solution, i.e. not sit down with your friend and compare your answers. I want you to get together and talk about the strategy and so on, because I like to propose homework problems that are challenging and sort of take the concepts from lecture and try to go as deeply and as critically as possible. So if, for example, you're not from mechanical engineering and maybe you haven't in some of these classes, meet others who might have the background and they can kind of help you think about it. As well, some of you say from material science or electrical engineering or other fields, there might be things that we talk about that you have the background from, so you can kind of trade that expertise with others. So I think one good way to feel like you're on a common and strong base is to team up with people from different departments, and that might also be an effective strategy when we start talking about the project. And also, with regard to grading, I've listed how the percentages will be laid out. I mean, I really want everyone to do well in the class. It's I can't say what the final average letter grade is going to be in translation to a percentage, but I could say if everyone does really, really well, I have no problem in giving a lot of A's in the class. If you think of how graduate courses are graded typically compared to undergraduate courses, if you're an undergrad, you might be more familiar with a core class being assigned a mean of like a B to a B minus, depends on the class. Given this is a graduate class, without saying specifics, I could be pretty sure that the average letter grade is going to be higher than you would find in an undergraduate class. So, I mean, if you're feeling challenged, and I think that hard work will pay off, and you all should do on average pretty well in the course, and I want you to do as well as possible. My goal is not, there's always a distribution, but the goal is not to take the distribution and shove it down to a particular level in the end. One more comment is I've decided, although not settled the details, instead of having a literature review assignment as I did in past semesters in terms of a presentation, given the size of the class, which is probably going to settle at about 40, I'm going to propose that instead be a team assignment where you take a lecture topic and sort of write that up and summarize that. So I'll announce those details, but just in reference to the syllabus, we're not going to be doing a literature review and so on. And then there's one final topic that I'm interested and willing to address if we have time, and that's the process that I use for searching literature and using things like literature databases and RSS feeds and reference archiving software. But I don't think we have time to talk about that in lecture. So what I'm going to ask you all now is if you're interested in this topic, would you be, and if your schedule fits, would you be willing to come for like an extra half hour and I can talk about that? So raise your hand if you would want to learn about that and come for extra time. Okay, that's good enough. So we'll schedule that, and I'll hopefully schedule it so it can be videotaped as well, and if you can't make it, we can have the video up on the course website. So that was listed in the syllabus as one of today's topics, but we'll hold that for now, and I'll let you know within the next week when we'll set that up. Okay, are there any other questions before we get into today's lecture material? Cool. And also, there's a lot of space at the front. Someone told me last time that it's kind of hard to see the slides at the back, so always feel free to sit up close. It might get harder because today I'm going to start writing on the tablet, and it might be a bit small. So I don't mind if you're feeling far away. You can come up middle class and sit closer. All right. So today we're going to talk about general classifications of nanoscale structures, sort of naming and taxonomy. We'll talk about a couple examples of scaling, really elementary examples, but starting to get in our minds the idea of how things are different at the nanoscale in the case of high surface areas and stresses and pressures introduced by the existence of a lot of surface. Then we're going to talk about what I think purely for us is a kind of mathematical concept, but this idea of magic numbers, that very, very small sizes, when you have structures that are so small they consist of discrete numbers of atoms, you don't see, if you're able to measure the size of all the little pieces you make, say if you burn something or you zap something with a laser, you don't see like some with 59 and 60 and 61 and 62. You might see way more with, say, 60 and way more with, say, 80. And we'll talk about how that relates to this concept of stability at the nanoscale. And then we'll spend the last section of the lecture talking about the structure of carbon nanotubes, which I choose to treat for two reasons. One, we're going to talk a fair amount about carbon nanotubes throughout the semester. And second, because there's so much interest in nanotubes and because of the way they're organized, researchers have developed a convention for naming their lattice structure and sort of denoting their structure and relating that to the properties. So we'll go through a bit of that. And then the readings for today, which are already up on CTools, I've put into three categories. We have a paper by Teo and Sloan on this idea of magic numbers, and this gets pretty detailed, and really here I want you to know the concepts only and the types of things we talk about in lecture, but you can flip through it as you want. There's a second paper on the structure of nanotubes, and this is something that we'll need to know in detail because there's going to be a question on the first problem set about it. And then for reference, there's a chart, which we'll see in the slides later, called the periodic table of carbon nanotubes, kind of put together by this company, but talks about the different structures and sizes of nanotubes. I have a few extra readings, some of which relate to the lecture, but more for your general interest, so you can look at those. And then in terms of sort of topics of background, I may be missing something from time to time, but we'll probably draw some general terms from knowledge of crystal structures, and in some cases, Wikipedia is a good reference, and there's a nice Wikipedia page on crystal structures, similar to what you might find introductory in a material science textbook. And then when we talk about nanotube structures, we're going to need some vector math, so sort of dot products and cross products. So those are other things that you might want to review if needed. All right, so today we're, I think, really going to start at the ground floor of the universe of structures that we're going to build upon. So this is actually a sign from a clothing store that I saw in Tokyo that, for some reason, I don't know, calls themselves the Nano Universe. They actually sell a lot of shoes and funny-looking clothes. So maybe they're making more money than nano people are making yet, but not in the future. In fact, when people started thinking about how materials and things are structured in 3 dimensions, there were some interesting geometric things that went on. So this is more of a historical reference than one to nanotechnology, but there's this idea, if you connect circles, drawings of circles in a plane, you can create projected representations of three-dimensional lattice structures. So back from a temple from thousands of years ago in Egypt, carved in stone, we found this sort of pattern of overlapping circles. And Da Vinci did a similar thing, patterning overlapping circles, and some people call this the circle of life, and so on and so forth. There are different terms that have been bandied about, but what we're interested in here is if you take these circles and overlap them, you can start to see the evidence of lines by connecting the centers of the overlapping circles. And in fact, you can use constructs of circles in this fashion to create projections of three-dimensional solids. And so these three-dimensional solids are called the Platonic solids, and there are a large number of these constructs. And I know that the details of these aren't important for us, but it's interesting that this is a geometric way you can use two-dimensional elements to construct accurate projections of three-dimensional structures. And it turns out you can use this process to create sort of these elementary volumes, which end up being reflected in some of the basic crystal structures of materials. And in fact, when we start talking about clusters, about halfway to 2/3 through the lecture today, there are actually some nanoparticles and nanoclusters that have shapes like this. And it turns out that the energetic stability of the facets and the discrete number of atoms relates totally to the geometry and the crystal structure. So I just think this is an interesting example of geometry and crystal structures and organizations of atoms coinciding. And you may remember from material science or sort of introductory materials and physics theory that if you have a solid material, the atoms in that material are arranged in a crystalline lattice, if it is a crystal. So at a fundamental level, if you zoom way in and look at the atoms, you can see the positions of the atoms, and because of the way the atoms interact with one another, they form a crystal. You may have, say, a large single crystal, something like a silicon wafer, where the atoms have a great degree of long-range order, or you may have a material that is considered polycrystalline, which might have a whole bunch of little small crystals that are all in different orientations. But if you get way, way down to the nanoscale, you're going to be able to identify each material as having a particular crystal structure. And in the formality of defining lattices, there's what's called a Bravais lattice, and there's a definition of a Bravais lattice which is based on the ability to use vectors to represent the positions of the atoms. And here, I just want you to know and appreciate that we can say that a particular material has a certain crystal structure and has a certain orientation of that crystal. So for example, we'll see that things like silicon, nanowires have a certain crystal structure, and they can grow in different orientations, and that crystal structure will be one of these lattices. Other things that are more specialized, such as nanotubes, may not fit into one of these lattice categories, but there are ways to represent it as a crystal, as we'll see later on. So there are, to complete this concept of these Bravais lattices, all crystalline materials can be found, that have a Bravais lattice can be categorized into one of 14 organizations. And you have 7 lattice systems, and then with particular lattice systems, you have different organizations of the atoms. You could say perhaps the simplest Bravais lattice is a simple cubic lattice, where you have, it's just like atoms in a cubic grid, and the atoms exist at the corners of the cube. And if you imagined taking 8 atoms and slicing through them, so you had a quarter, or I guess that would be an 1/8 of each atom at each of the corners, that would define the unit cell. So the idea of the unit cell is the smallest repeating unit. So you can take a whole bunch of unit cells and you can stack them up like stacking up little building blocks, and you can make a larger and larger crystal. And then there's body-centered cubic and face-centered cubic, where in body-centered cubic you have an atom at the center, and that's sort of all you add here. And in face-centered cubic you don't have an atom at the center, but you have atoms at the faces. So in each of these cases, the unit cell would have a different number of atoms. And we're not going to go through these, but you might hear these terms as we go on, and you could look back and look at these structures. And there are also, you could say, more complex or intricate organizations of atoms that satisfy this Bravais definition, and this completes the set of 14 that exist in this way. So, as we try to get our brains thinking about things at the nanoscale, if we want to calibrate ourselves, we talked briefly about last time about how the length scales of things compare. So remember that human hair is tens of microns in diameter, and things that are at the atomic scale are on the order of nanometers or fractions of a nanometer in diameter. And some biological things, for example, the size of a cell is approximately, you could say, 1/10 the diameter of your hair, or approximately 1 micron in size. Certainly different types of cells have different sizes, but that's a good order of magnitude. So probably a lot of you are on top of this already, but there are basic length quantities that should be hardwired in our brains, because we're going to talk about microns and nanometers and angstroms back and forth. So you should be able to roll these off of your tongue. So 1 micrometer, or frequently called a micron, is a millionth of a meter, or 10 to the minus 6 meters. So the micron is right down here, about the size of the cell, and that's just a bit larger than the wavelength of visible light, which, based on the color, has a range, but is about half a micron. And then 1 nanometer is 1 length scale beneath that, so a nanometer is 10 to the minus 9 meters. And then the smallest quantity that we're going to typically talk about is an angstrom, and that's 10 to the minus 10 meters. So it kind of doesn't fit in this, a 1,000 space, but that's 1/10 of a nanometer. So we can say that a millimeter is 1,000,000 microns, a micron is 1,000 nanometers, and a nanometer is 10 angstroms. And sometimes I'll probably just type with the A because it's easier in Word, but typically you have an A with a dot on top as the symbol for angstrom, but A is fine for what we're doing. And approximately, as an order of magnitude, you can always think that the spacing between atoms in a typical crystal is about an angstrom, about 1/10 of a nanometer. In carbon lattice, it's about 1.2 angstroms. It's going to vary, but fair enough. It's just good to know that and to say that. So, with this grasp of the length scales and the types of crystal structures, now we're going to move away from the bulk scale down to the nanoscale, and we're going to start to categorize the types of structures that we're going to learn about, and we're also going to use as examples for studying properties and synthesis. So last time I showed you a variant of this slide where I'm starting to classify nanostructures based on their geometry, and that's then going to relate to their properties. So in the field in general, we talk about zero-dimensional structures, or things that are generally round and very, very small, as being called nanoclusters when they have these small numbers, or can have these magic numbers of atoms. And typically, those are around a nanometer or smaller in size. Something like the C60 molecule having 60 atoms, and it's about a nanometer in diameter. Now, if we take the same size and we go up a bit, so we're beyond this idea of magic numbers, or we're in a range where you could still apply this magic number theory, but the numerical spacing between the numbers will have a negligible effect on size. We get into the nanoparticle range where we have, you could say hundreds to thousands of atoms, and the diameter is, say 1 to 100 nanometers, just as loose boundaries. And so that completes the set of zero-dimensional structures where the properties are going to depend strongly on, of course, depending on the material, the size of this volume and the diameter of this cluster, or the diameter of the particle. And then, if we look at one-dimensional structures, we have nanowires and nanotubes. The difference being whether they're filled or they're hollow. And you can start to see resemblances between the schematic pictures here, or the real pictures here, and the types of lattices that we saw on the previous slide. So you could look at this and actually use X-ray diffraction or electron diffraction, which we'll talk a bit about in the next lecture, to determine the crystal structure and the crystal orientation of the atoms in this lattice. And although they have some defects, we can see that they have pretty regular organization. And then a modification to what I showed you last time is classify another type of structure as a sort of two-dimensional nanostructure, and this is a sheet, something such as a single layer of graphite called graphene, or a single layer of clay, as something that has sort of a two-dimensional organization. So it can be considered a two-dimensional material with zero thickness and properties defined by the characteristics of the plane. And in the case of single-layer graphite or graphene, there's a lot of research going on now about the electrical and other properties and mechanical properties of this arrangement of atoms. And we'll talk a little bit about that. But sort of 0D, 1D, and 2D in kind of a different sense than we would think at the large scale, but let that be our nomenclature for moving forward. So we'll treat a number of examples of different types of structures depending on how much we talk about their properties. So one type of nanostructures that's studied widely are nanostructures or nanocrystals made from zinc oxide. Just when you have it stoichiometric, you have one atom of zinc for every atom of oxygen. And so here's a scanning electron microscope image of an array of zinc oxide nanowires that are grown on a substrate. And when you grow them, as we'll learn later, they grow in a specific vertical orientation because of a relationship between the crystal structure of the zinc oxide and the crystal structure of the substrate. In this case, these were grown on a particular orientation of single crystal sapphire, or Al2O3. And so these are individual nanowires that have a diameter of, say, a few tens of nanometers, and you can already see that there is a diameter distribution. Some are wider than others, and some are taller than others, indicating the uniformity in the process and how the growth rate may depend on the size. And if imagine we were able to sort of break this up and pick one of them out, we could look in a transmission electron microscope, and we could isolate an individual zinc oxide nanowire, and we could then use the techniques we'll learn about next time to look at the structure. And with other techniques, you can, for example, take projections and see how the walls are faceted and so on. But I'm showing you this now to emphasize that we can use imaging tools to look at the positions of the atoms and get basic parameters such as that lattice spacing. So the distance between, we could say, rows or planes of atoms in this projection in different directions. And I can also use diffraction to get spots, and you'll see the origin of this on Wednesday, that let us decide what crystal structure this is. And it turns out that zinc oxide has what's called a hexagonal wurtzite structure. So it fits in the hexagonal category of the world of lattices. And this actually consists of sort of stacked tetrahedra of zinc atoms and oxygen atoms. And the way the atoms are laid out, you have zinc with a 2+ charge and oxygen with a 2- charge. And because of the way the polar nature of the atoms affects the growth process, that can let us grow zinc oxide nanostructures in a variety of different shapes, as we'll see on the next slide. And because of the structure, the properties of the individual atoms and how they're hooked together, this makes zinc oxide a semiconductor, and it also makes it a piezoelectric material. So if you take one of these zinc oxide nanowires and you bend it in one direction, you actually can measure a voltage on one side of that wire, because you're taking these charges. If you're straining the lattice, you're taking charges and you're moving them physically apart from one another, and you're therefore creating a voltage. And there are some interesting devices that are actually starting to harness these native characteristics of the nanostructures. But showing you this now, I just want to give you an example of going from a bulk crystal structure, to the structure at the nanoscale. The properties we'll really start talking about more later. And it turns out that with zinc oxide, because of the relationship between the way it's fabricated at high temperature and this crystal structure, you can make zinc oxide nanostructures having all these different nanoscale forms. So sometimes you get these kind of comb structures. Sometimes you can make these discs. In other conditions, it will grow in hoops, or it will grow in belts. And this just relates how the atom's organized to basically how the crystal forms and what sides of it are stable and what sides of it are not stable as it grows. And this picture will become clearer when we talk about how the structures grow in about I guess 4 to 6 weeks from now. But for now, just appreciate that you can have say zinc oxide, which has a particular crystal structure, and based on how you make it, and you can make that crystal structure into a whole bunch of forms. And instead of having, say, a block of zinc oxide that might, have these hexagonal domains in different orientations, you can have what are essentially single crystals that grow in particular directions and create all these different types of things. It's in some ways analogous to the people who look at snowflakes see that snowflakes can have different sizes and shapes, and you hear like no snowflake is ever the same, but there's a lot of inspiration from crystal growth and how snowflakes form and how the conditions, the temperature, the pressure, the rate of cooling affect how the crystal forms, and kind of similar things are seen in how some of these nanocrystals form. And what we're going to see is the unique connection to the properties of the structures. And there are also ways, as we'll start to talk about synthesis later, to sort of create what are called heterostructures, or combinations of materials, or things that may not directly come from the way the material self-organizes. And this is an example of what's called a Coreshell nanowire. So made by a process like I briefly overviewed last time, where you imagine, we're all sitting in a big furnace and we spray in some small particles of gold, so some gold nanoparticles. And remember, we fill the room with a gas that contains silicon, this material that we want to grow, and basically start producing a nanowire using this gold particle as like the little reactor. And what this group is doing is they're growing, for example, this silicon wire first, and then they're changing the precursor atmosphere, changing the source gas, so you then deposit another material on the surface of the wire, and then they can change it again so they can sort of stack the wire radially and say, make this out of materials with different dopant levels to make one an N-type semiconductor, and then one a P-type semiconductor, another one an N-type semiconductor. So, and they can do the microscopy, kind of as we saw for the zinc oxide nanowire before, and now to see that here they're making actually a germanium core, and they're putting silicon on the outside and using techniques that let them image which element is where. You can see that you have, in this case, a higher concentration of one material at the core and a higher concentration of the other material at the shell. This is just a radial scan from the outside to the inside, and the outside quantifying the presence of those two atoms. And they can, for example, although it's sort of very painstaking and requires advanced lithography, can connect one of these structures as a device, and in this case, making electrical contacts to it. This is just, of course, a solid model, a schematic, but they were actually able to do it, where now they can make one contact to the outside, and then at the ends they actually etch off the outer layers chemically, and they can make electrical contacts to the inside on both ends. So this is a type of electronic device that we'll talk more about later, but it's an example of structuring the material in another way using the characteristics of the synthesis process. So in addition to the things that result from the basic structure of the crystals, we see researchers trying to sort of create synthetic architectures by controlling the synthesis process, and now taking advantage of, for example, the unique properties of these two different materials, silicon and germanium, when they have very, very thin layers at intimate contact. And now you can already start to see sort of the manifestation of imperfections. This is not perfectly straight, or maybe because you're going to get some diffusion of the silicon into the germanium, this is not an abruptly atomically sharp interface. Also the technique may not be able to detect that atomic sharpness, but there's certainly some mixing going on, and that has an effect on the properties of the structures. And there are, sort of, endless varieties of building blocks, and there are also ways, as we'll see examples throughout, to make, for example, branched structures. I think we saw a bit of this with the zinc oxide and certain growth processes that, if you have a crystal with a few different directions, and if the stability of one space or one side is higher than the other, then under some conditions you may, you may get it growing in one direction but not the other, and that, for example, can lead to some of these unique types of branch structures. And in this diagram, they're just really showing things with no similarity other than their size and a maximum diversity of shape. But under different processes, people are trying to make sort of clusters of particles, or particles with a small one docked against a big one, or things like cubes and triangles, or rods or stacks of rods, or even, for example, studying how molecules will self-organize on very small curved surfaces. And this gets to ideas of energetic stability and surface energy that we'll talk about later. So this is sort of more of a preview slide of showing the kind of diversity of things that might be possible if you can understand how the molecules hook together and what's stable and what's not stable at this scale. And these, in many cases, directly are motivated by the types of properties or the types of interactions that might happen. For example, it's possible to get very, very strong fields or a lot of energy if you take two structures that have very, very sharp tips and bring them in close proximity. Or if you get two different materials that are the right materials, such as gold and silver, together at an interface. So that could be some motivation for making these, one particle docked against the next one, and so on. Or things like precise arrays, things like that. Or, for example, figuring out how to pattern surfaces so you can get different regions of different characteristics. If, for example, I was able to, say, pattern this nanoparticle with two molecules with two different chemistries, maybe you could prevent it from sticking to something because whatever wanted to stick to the particle wouldn't have enough of the molecule it likes in, to be able to latch onto it. And those are things that a lot of people are studying as we speak. So if we look at, what I think is probably the most, basic and simple concept of things at the nanoscale, and I'm going to, forgive me as I figure out how to use this thing once again. Speak up if things are not clear on the pen, but I'm going to do all my writing on the screen so we can have it captured, and also so it can be seen on video. But if we look at, for example, a sphere which has a radius r, and we just calculate the ratio of the surface area to volume, we have the surface area of a sphere is just 4 pi times r squared, and the volume is 4/3 pi r cubed. If we cancel what we can, the pi's go away, the 4 goes away. We lose the r's on top, and we lose all but one of the r's on the bottom. And this is equal to 3 over r, or 4 divided by the diameter. So, of course, the idea here is that as the diameter decreases, or the radius decreases, then the surface area to volume ratio goes way up. That's right. Thanks. And so you could do this for a cylinder, you could do this for a cube, but can someone tell me, maybe what's a practical manifestation of this? What might be different between a surface atom and an atom in the bulk?
Outside, where ones in the bulk don't.
Okay, so they have kind of a different physical experience. Anything about the actual configuration of the atoms on the surface versus inside the bulk?
Bonds.
Yeah, so the bonding configuration may be different. If you're inside that that cubic crystal, you're going to have atoms connected to all. But if you're on the edge, then you're certainly going to have some reactivity, some openness. And those are both good answers, and they relate practically to how nanostructures can behave differently with their environment, how their properties can change with size, and also how it might be difficult or more challenging to process them because you have to deal with all these surface atoms, the fact that they stick to each other, and so on and so forth. So recall from the slides last time that the number of atoms can be counted as you get down to the nanoscale, and if we think that we're down at this scale of having, say, 100 to 1,000 atoms, if we look at a different kind of simple plot for a sphere where we look at the percentage of surface atoms versus the total number of atoms, you see that if you're in sort of the nanometer size range, you have maybe tens of percents of your atoms on the surface, and that has a big difference on the properties and the characteristics of the structure. So, without too many specific examples, one thing that makes a difference is because each atom in the material has electrons that are swimming around it in the orbitals and the specific energy levels. There is an electron cloud around the surface of the particle or the surface of the material, and if you measure the local density of charge as you move say from a small distance away to it, you would see some distribution and in fact some oscillation of the charge density as you move. In this case, this is really a schematic drawing representing a general metal, but this length scale is meant to be the distance divided by a length scale in angstroms, and in this case the material has a unit cell spacing, a unit spacing of 1 angstrom. So this is just a very general representation of what could happen electrically at the surface. And in some cases, another thing that happens is that, as I alluded to before, in crystals that have anisotropic organizations of atoms. So imagine, say the spacing from one atom to the next is different in different directions. Some surfaces are more stable than others. So one thing that happens, for example, is silicon. If you have a 1,0,0 surface exposed, then 1,0,0 is just a representation for a particular direction in the crystal. So if you read again about crystal orientations and Miller indices, you'll quickly know what this notation means. Just as an example, if I take a crystal of silicon and I crack it in this direction, the atoms on the surface will reorganize from this configuration to the other configuration. So you go from having a flat surface, which represents the bulk crystal sliced up, to the bulk crystal beneath it, but the atoms move over and form these grooves on the surface. So we don't need to know entirely why, but I just want you to appreciate at this point that the surface is very special and important in governing the properties of a lot of different structures. And if you think of transport of heat or electrons through a nanostructure, a nanotube, or as nanowires, we'll see starting next week, how the atoms are organized at the surface. Or, for example, if you're operating in air, if you might get something from the air sticking to the surface, that can actually interfere with the electrons and the vibrations going through the structure and have an effect on the properties. And those are things that are, in fact, readily and frequently measured and can be interesting findings and also problems for when these devices are made and characterized. So another thing that I want to think a bit about is we'll talk quite a bit in a few weeks about the idea of a surface tension or a surface energy, and we'll relate that to, for example, why small particles of metal melt at a very much lower temperature than the bulk. But you probably remember from fluid mechanics this idea of a surface tension, and so if we consider that we have our sphere again with the radius r, and now imagine that we cut our sphere in half, and because we cut it, like mechanical engineers, we want to draw a free body diagram. And so we're going to say that around the line, around the perimeter of the sphere, we have a surface tension which we're going to call gamma, which has units of force per length. And then if we sort of sum the total force around that line, that would be F gamma is equal to just the distance, 2 pi r, the circumference, multiplied by gamma. And so if this body is in equilibrium, it's sitting in some atmosphere with some pressure. So we have pressure on the outside, which we'll call P outer, and we have a pressure on the inside, which we're going to call P inner. So for this body to be in equilibrium, we want to sum the forces on it and have the forces sum to 0. And if we take, for example, forces, say in this direction downward to be positive, we have the surface tension force being positive, so 2 pi r gamma. And then we have the pressure force, the net pressure force on the outside being positive, which if we assume the pressure is uniform and we just take the projected area of the sphere upward, that's P outer times pi r squared. And then we can subtract the inner pressure, Pi times part r squared. And then we would collect terms to one side. So we could say minus 2 pi r gamma equals P outer minus P inner times pi r squared. And if we solve this out and cancel like terms, we would get that P outer minus P inner is equal to minus 2 gamma divided by r. So now, not yet knowing the origin of this, or what determines the value of this gamma, we can see, based on this simple model of something like an inflated beach ball, that the difference between the outer pressure and this internal pressure is inversely proportional to the radius. So you might remember this from things like liquid droplets, and if our droplet's something like a millimeter in size, this isn't a big difference because of the ratio of gamma to r. But if we're down at the scale of a nanometer, there is a big difference between the pressure inside and the pressure outside because of this surface tension. And I don't want to leave too much of a sort of a mystery here. You can think of one origin of this surface tension being those unsatisfied bonds we talked about. And that means that there's actually a difference in the forces between the atoms because they're not fully bonded compared to the ones in the center. There's also kind of more asymmetry because if you're in the center, everything is sort of, you could say uniform in all directions, but if you're on the edge, things aren't quite so uniform. And you can make a similar or sort of a slightly more complex derivation for a bulk crystal that relates to the mechanical properties of the crystal. And I won't go through this in the lecture. It's in the notes, but it's not something we're really going to need for the problems we're going to solve. But you get a slightly different expression that can express the actual contraction in the lattice spacing as a function of the surface tension or the surface energy of the crystal. And now I brought this up for general intuition, but because I wanted to show you this data, which actually shows that because imagine you have, say, gold, which for now we could say any piece of gold has the same surface tension, but you measure the lattice spacing A. So this means if you have a crystal, and now I'm just going to represent this crystal as having a simple cubic lattice. A would be the lattice spacing. It says on the vertical axis here that as the radius of the particle changes, the lattice dimension changes because of this effect of size on pressure. And you can see that these changes are pretty small. G, we're looking at 0.4 nanometers or 4 angstroms here, and it's like 0.0406 to 0.408. But there is a change, and it looks like a pretty linear trend. And this also shows that using a diffraction or using the interaction of X-rays with the material, you can get a pretty precise measure of the spacing. And this is simply as the particle gets smaller, this is inverse dimensions, there's more pressure inside, and therefore you're physically squeezing the atoms closer together. And what can be done in more detail is these researchers have also plotted, for example, the change in this local spacing as a function of the distance from the center of the particle. So now this is no longer the radius or the diameter, it's how far you are from the center of the particle. So it shows that at the edges of the particle, the lattice spacing is smaller than in the center because you have more of a local effect of this surface pressure. So there are manifestations of this surface stress in changing the positions of the atoms and what they're locally feeling. So there are certainly here differences between what the surface atoms feel and what the bulk atoms feel as well. Okay, so now I want to get into a bit about this idea of clusters, of structures that are so small that you're sometimes observed having specific and special, numbers of atoms. And so as a formal definition, I say it as exactly that. Clusters are, materials like C60 that are more frequently found with specific numbers of atoms. Then the reason why is that they are sort of geometrically closed shells. So if I imagine this C60 particle, which had a bit of an accident on the way over here, there are exactly 60 atoms here. How am I going to fit in atom number 61? Well, I have to open up this bond, and I have to jam in a seventh one here. And as you can see, it's going to be, difficult, and there's going to be a cost to that. So there's some nice perfection about this organization of 60. And in the supplementary readings, I think this is just for fun, there's an article written by Rick Smalley who discovered C60 with two others and actually won the Nobel Prize for it. And he talks about how they found C60 in the lab using this sort of cluster apparatus where he evaporated carbon and then measured the sizes of the different clusters. And the other fun part of the story is he talks about how he realized that this is actually the structure, because on their instrument they just saw a peak that said, wow, there's a whole bunch more 60 than the rest. And he says he was like at his kitchen table at midnight one night playing with paper and making paper hexagons. And knowing that carbon, like graphite, is hexagonal, he was trying to put hexagons together, and it really didn't work. So all of a sudden he realized that, oh, what happens if I add some pentagons? And he found, believe it or not, that if you put pentagons and hexagons together, he got the C60. So it was like after midnight. So Harry Kroto, his collaborator, was in England, and he picks up the phone and he calls Harry Kroto, and it's like first thing in the morning, and that was it. They had the sort of eureka moment where they had discovered the special structure of C60. So I think it's just a fun story. But where we're going to take this fun story and start to think a bit geometrically is this idea of sort of so-called magic numbers. And the magic number is something like 60 for carbon, where a cluster of 60 for planar carbon is special because of its stability. And this structure, this idea of magic numbers is talked about in the Teo and Sloan paper, and we'll just spend a few minutes talking about a couple of the concepts in this paper. So, this is, for us, I think, just kind of like a little geometric and mathematical exercise, but I want you to use it to think about the relationship between this idea of bulk crystal structure with atoms in different prescribed positions, and the fact that if you start imagining us taking individual atoms and building them up like blocks, the fact that you're going to have say one to start, and maybe if we're working in a plane here, so imagine a two-dimensional world, what's the next thing I can do and have, quote, a closed shell? Well, if I'm making things out of triangles, the next thing I can do is add two more, and I'll have sort of one triangle. And then to make a bigger triangle, I have to add 3 more and 4 more and so on. And so these, by the the definition of magic numbers, would be the numbers for triangles in 2 dimensions. So just 1, 3, 6, and then 10. And we're not going to talk really about clusters that have 10 atoms in a plane, but we're going to talk about the concept of having things like 60 or a few hundred and the fact that they occur. But what this paper does is it develops sort of the mathematical formalisms based on series math for denoting how the atoms add up when you go given a particular lattice. So in this case, our lattice here is a sort of planar set of triangles, but they go into all the more complex ones that we've seen already, and how the magic numbers pop out. So in the formalism of the paper, if we start building atoms in this way, if we look at the number of atoms in the 3 cases here, well, there's 1 here, and there's 3 here, and there's 6 here, and there's 10 here. And then the paper defines small lowercase n as what's called the frequency as being 0, 1, 2, and 3. So the frequency here is this number, sort of nu sub 0, 1, 2, 3. So you start at 0, and each time you add another, quote, level, another, you could say another row of atoms in this case, or another plane of atoms if we're in 3 dimensions, you step up to add one number to that. Switch this out? Sure. So just want to spend a minute and sort of tell you, and you'll see this if you look through the paper, if we extend this concept to, we're going to remain in 2D, but we'll say we have a generic polygon, and we define F as the number of triangles. So any polygon in the plane we can decompose into a specific number of triangles. And we say P is the number of sides of that polygon. And then we say N is the frequency as we define for the triangles. Then it can be calculated that the total number of atoms in this polygon, which the authors call capital G sub n, so for a polygon of frequency n, is equal to 1/2 capital F n squared plus 1/2 Pn plus 1. And then the number of surface atoms, or capital S sub n, is equal to just the number of sides times the frequency. And then if we take G and subtract S, then we get the number of interior atoms. And that is just, we'll call this, sorry for running out of space here, capital I sub n, and just subtracting G minus S, we get 1/2 Fn squared, and then minus 1/2 Pn. And then we retain the plus 1. And so if we had, for example, a pentagon, and we started with one atom in the center, and I draw the best pentagon I can from that center, and then I drew another pentagon out here, and trying to keep, the side length of all the triangles the same. That's a bit imperfect, like so. So I have one atom here. Maybe I'll try to change the color. So I have one atom at the center, 5 atoms around at this first level or at this first frequency. Sorry, I missed a line there. Then I have another set of atoms here, and also I'm introducing another set of atoms here because I'm keeping the atom-to-atom spacing the same. It should be that way, although it doesn't look like that. And then in the way we wrote out the notation, so this would be n equals 0 and a total number of atoms of 1. If I have a pentagon that sort of has this one level or this frequency of 1, n equals 1, and then G sub n equals 6. And then at this next level, I have n equals 2, and the formula would give me that the total number of atoms is 16. So if I looked at the formula again, it would be 1/2 Fn squared plus 1/2 Pn plus 1. So in the case of this n equals 1, I have 5 sides, so I have 1/2 times 5 times 1 plus 1/2 times 5 times 1 plus 1, 2.5, 2.5 plus 1 equals 6. That's 6. And if I count the atoms, I get 6. So maybe this seems a bit abstract, but if you look at the paper, you'll see that the same idea of starting at 1 and going to another level, or one more frequency and another level, can be applied to all the basic crystal lattice structures that we showed at the beginning, and you can derive the actual magic numbers for different sizes of these different crystals. And believe it or not, that's what's seen in things like titanium or gold. Based on their lattice structure, if you do a measurement of the stabilities of the different crystals, you see that you have a predominance of these of some sizes versus the others. And this could be extended. For example, we could do the same thing without taking the time to do it. If you had, for example, a tetrahedron, so a three-dimensional solid, and we had our frequency in that case would be sort of 0, 1, 2, and now each floor, or each floor here would be a series of triangles, and you would just do the math in a more complex fashion. And a lot of these formulas come from looking at series summations for some n plus n times n plus 1, n plus 2, n plus 3, and so on. So that's the kind of math that leads to this. But sort of this idea of surface atoms and interior atoms, or edge atoms in the case of two-dimensional, can let us derive the numbers that we'll see in some of the cases of these cluster experiments. And here's just an example of how we would go through pentagons, or how you would go if you had hexagons, and depending on what the eventual structure of the lattice is that you want to create. So this is all in the paper that you'll get to look at. And similar thing if you went through the triangles, tetrahedra, that's a lot better than I tried to draw, and also for say an octahedral crystal structure. So this all is laid out for you. And for example, measurements of clusters made of titanium and nitrogen, so titanium nitride, where you have 1 Ti for every 1 N, and these have a simple cubic lattice where you have alternating atoms of titanium versus nitrogen. If you make clusters, you basically evaporate the material, vaporize the material, and condense it, and you look at the this is a spectrum that shows the intensity. It's basically a signal which corresponds to the frequency of particles with a certain size. You see the predominance of these different clusters. So in the case of a cubic lattice, imagine that you have, quote, a magic number if you have a flat-sided box of any particular size. So it doesn't necessarily have to be a cube. You just have to have something that has flat sides on all faces. So it can be say like a flat gift box, or it can be a perfect cube, or so on. And so 3 by 3 by 3, 4 by 3 by 3, 4 by 4 by 3, all these actual mass units or number of atoms correspond to closed structures. And you certainly see some presence of things that say have, for example, this atom missing, or have a little bite taken out of it, but because they are less stable, because you have those surface atoms exposed, it might, for example, that might be an initiation site for this whole row to be eaten off and to form a smaller cluster. And another thing that is important to note from a qualitative basis here is that the relative abundance of these magic clusters is greater when they are smaller, because from an overall point of view, if I have, say, a 6 by 6 by 6, which is what, about 200 atoms, adding or subtracting a couple isn't going to be a big difference in the overall stability of the structure. So I'm going to have a smaller relative abundance. But if I have like 3 by 3 by 3, taking 1 out of 9 atoms away is a big deal, and that means that you're going to be more preferentially, you're going to have 9 instead of 8, but less preferentially have say 200 instead of 199. So you also see that expressed in the experiments like so. And sort of as just a flavor, how these kinds of experiments are done. This is from a different paper than the previous results before, is, for example, using a laser to, say, vaporize, or a heater to heat a particular material. So, your titanium nitride, say, powder, could be sitting in a little container, and at very low pressure, if you can vaporize it and then basically drive it down a column where you know the relationship between the time that different clusters or different sizes will take to fly to a certain destination, because their speed is going to depend on their size. You can electrically detect the arrival of clusters of certain sizes, and you can create that spectrum that you see there. So, further details aren't important for us now, but this kind of concept of sizing molecules or sizing clusters or sizing gas molecules is really important for determining the specific sizes and distributions of sizes of materials. And we'll see examples later on of the techniques like centrifugation, where you, for example, can distribute spin liquids at speeds and get sort of equilibrium in solution, and therefore you get structures of a certain size or a certain charge in a particular region, and that's, for example, a means of separation. So better techniques of measuring or separating structures of different sizes are also really important and useful. And if we go back to our idea of the platonic solids, in fact, for gold nanoparticles, the paper will talk about how gold nanoparticles have an FCC cubic structure, and it turns out that the FCC crystal structure corresponds to a cuboctahedron in the platonic solid world, and each of these solids, sorry for going back, has a magic number of atoms because it's closed. And G, here the paper computes the magic numbers of atoms, the bulk atoms and the surface atoms, and this is actually what is seen for nano clusters of gold at these small sizes. So there is a very beautiful connection between what we started with and what we're ending up with here in terms of how small numbers of atoms are stable and how we can quantify precisely the number of atoms on a surface, and how that relates to the way the atoms want to organize and be stable in the first place. Okay. Are there any questions about clusters? All right, so we have about 15 minutes to go, and I think that's enough time to talk about the last topic, which is the structure of carbon nanotubes. And carbon nanotubes are an example of what are called one of the allotropes of carbon, allotrope being sort of a physical organization of what is the same material. And in the carbon world, there's graphite, which is planar sheets of carbon with the atoms in a hexagonal configuration. There's nanotubes, which are sheets that are sort of seamless in cylinders. You can have single-walled nanotubes and multi-walled nanotubes, and they can have different properties, as we'll talk about later. There are fullerenes, and C60 is not the only fullerene. Following along the same lines as we had for the titanium nitride clusters, there are other clusters of carbon consisting of pentagons and hexagons that have these closed shells. I forget what the numbers are, but I think it's like 96, and there's one in the 120s, and the smallest one is something in the 20s. So you also have different fullerenes of different sizes. And then there's also bulk carbon, or diamond, is in what's called the diamond lattice, and here is the representation for the unit cell of diamond. So I'm showing you this as another example of sort of this idea of structural diversity, and we'll see later on how give more information about how these different structures are synthesized. But what I want to talk about now is the way that we understand the structure of carbon nanotubes from an approach that's inspired by crystallography and inspired by the idea of representing a crystal based on vectors and representing the placement and the orientation of the atoms using a vector system. And this has been devised because you can make nanotubes in a whole bunch of different orientations. And now, for the sort of sake of imagination, let's visualize a carbon nanotube. So now we're going to forget about the cap. We're just going to assume we have a tubular section. And let's imagine making a nanotube as taking a single sheet of graphite where you have perfect hexagonally organized atoms and rolling it up into a cylinder. This is not how nanotubes are made. Nanotubes are made by typically kind of that extrusion process like we saw for the nanowire, but that doesn't matter now. And clearly, we can think of rolling up this sheet of carbon paper in a whole bunch of different orientations. So you can roll it up, in this direction, where your axis is parallel, central axis is parallel to, you could say, the straight bond here, or you could roll it up in this axis where you're perpendicular to the straight axis here, or you could roll it up at any angle in between. And so the really only important geometric condition is that if we want to make this really a seamless and perfect cylinder, we have to choose our angle so when we bring one edge to the other, the atoms match up. So there's some discrete set of angles where you can get perfect matching. And the existence of defects complicates that, but for now assume we have this perfect lattice. And so now we want to develop a way to denote this rolling angle because, as we'll see later, the properties of the nanotubes depend on how we roll up this graphene sheet, or because we're not rolling up, just depend on the orientation of the axis of the nanotube with the lattice. And that relates to the whether tube is metallic or semiconducting, relating to how the atoms interact electrically, how the electrons behave based on their configuration. So we'll talk about those properties later, but now we just want to kind of formalize the idea of a nanotube lattice. And you'll see as you read about nanotubes that this orientation is typically called an armchair nanotube. And the way I like to remember that is if you imagine you have the nanotube vertically, and you're sitting on the top here because this exposed bond is flat, you could maybe sit down pretty comfortably. This one is called a zigzag nanotube because it would hurt to sit on this sharp little point. And these intermediate nanotubes are called chiral nanotubes, and this leads to the idea that the chirality, like you might remember from chemistry, the chirality is sort of the molecules that are different depending on their orientation, but have the same chemical structure. This is all carbon, but the chirality is this angle. And so this is an example of a chiral nanotube. It also has some defects and some shipping damage, but you can see the kind of helical winding of the carbon atoms relative to the lattice. So in the case of doing this, flat to tubular, or you could say, 2D to 3D transformation, we can make a few definitions. And this is described in good detail in the Charlier paper, which is on C-tools. And the first thing we're going to define is these unit vectors. And so on the hexagonal plane, we define two unit vectors, A1 and A2, and we consider each carbon nanotube as a linear combination of those vectors. So loosely I'm going to call a nanotube a crystal, and we're going to call each specific orientation or rolling of the sheet into the nanotube as sort of a different crystal orientation, or a different crystal, you could say a different specific crystal structure. And the way we go from these unit vectors into the actual nanotube is imagine making the nanotube by taking a strip of your lattice, like so. So imagine you have your sheet of paper. You decide the way you want to roll it. You take out your nano utility knife and you cut the sheet like that, and then you roll it up and you glue it together. And I define a vector, which I'll call C, or a fully C sub h with a little vector arrow on its head. And we're going to call this the circumferential vector or the chiral vector. and this is the waistband of the nanotube. This vector has a length equal to the circumference of the nanotube, so its length divided by pi is equal to the diameter of the nanotube. And remember, to make this work, I have to choose these lines so my atoms match when I hook my piece of paper together, but assume I did that. And then I can say that this circumferential vector, c sub h, is equal to an integer, n multiplied by a1 and m multiplied by a2. And these numbers, n and m, are what are called the chiral indices of the nanotube. So if we look at how nanotubes are named, you'll see, for example, you have a 5,5 nanotube or a 3,5 nanotube, and that represents specifically and exactly how the hexagons are oriented with respect to the axis of the tube. So this 5,3 nanotube is exactly what happens, what you get when you take the hexagonal sheet and cut it in this direction, such that you have taken such that the circumferential vector represents 5 steps in the A1 direction, 1, 2, 3, 4, 5, parallel to A1, and 3 steps, 1, 2, 3, parallel to A2. And that's a 5,3 nanotube. So then we can say that this vector c sub h is equal to n times a1 plus m times a2. And a1 and a2, as you can see from here, are the same length. So length of a1 is equal to the length of a2. And that is equal to the square root of 3 times what I'll call ACC. And ACC is the carbon-carbon bond distance. So this distance here is ACC. And so this is equal to about 2.46 angstroms. So that's about a quarter of a nanometer. And if you work a lot with carbon materials, this is sort of a number that, like definitions of length scales, you have set hardwired in your brain. Question?
ACC is 2.46 or ACC is?
Yep. So root 3 ACC is 2.46. ACC is about 1.44 angstroms. Other questions?
Square root of 3 is 1.732.
Okay. So I think root 3, 1.7 times 1.44. Is that about right?
Yeah, that's about right.
I can't do it in my head.
Yeah, no, that's right. I didn't realize the carbon-carbon bond was so short.
Yeah, pretty short. I have to double check on the chart. Yeah, so the periodic table, which we'll see at the end, has a nice summary of all these things. The ACC is 1.42 in graphite and about 1.44 in a carbon nanotube, because you have this surface effect, because you have the stress necessary to actually, although you wrap it up when you create a tube, there is the bond distance actually depends on the diameter of the tube slightly, and we'll see that later in terms of mechanical properties, but it's just like we saw for gold. So with this idea of n and m and the a1 and a2 vectors and the circumferential vector, we can start to do a bit of math. So now imagine that we have our waistband for our nanotube, so our circumferential vector ch. So this is kind of like the strip we cut before, and say this is an angle which I'm going to call gamma, and this is a vector which is NA1, and this is a vector which is MA2. So it's just a bad drawing representing exactly what we saw on the previous slide. So what I want to do, yeah, yes, it's perpendicular to the top, exactly, and it's exactly around the axis of the tube. And it should have said that by its definition, it has to connect one carbon atom to another carbon atom. No matter how far that atom is away, it has to start at a lattice point and it has to end as a lattice point. And therefore, when you bring one end to the other, it connects atom to atom. And any combination, by the definition of the unit vectors and the lattice, any linear combination of A1 and A2 will get you to another lattice point. And so that means that any CH and A1 plus MA2 will end up at the position of another atom, and that's why we choose the unit vectors to be as they are. So this is just a triangle which has an angle gamma, and gamma, because of the definition between of A1 and A2, remember they were 120 degrees apart, gamma is 120. So what we're doing here is I just want to find the length of the circumferential vector as related to these two vectors. So we can use the law of cosines for this, which just says the length of the long side of the triangle is equal to the square of the sum of the squares of the lengths of the two other vectors minus twice the length of the first one times the length of the second one times cosine of the angle gamma. And gamma is 120, so cosine gamma is minus 1/2. And we're going to call the length of A1, which we know is the length of A2, as just A. So that's different than ACC. Remember, A is 2.46 angstroms. And if we did this out, because we're running out of time, I'm going to skip a step, but I think you could follow through, because you can see that if this is just an integer multiplied by A, so the result here is just n squared A squared. Here you would have m squared A squared, and you would have similar things here with the cosine, and we would get a final answer that the length of the circumferential vector squared is n squared A squared plus m squared A squared plus 2n m A squared times 1/2, because I canceled the negative signs. And then if I simplified this expression and made the definition that the diameter of the nanotube is equal to the length of the chiral vector divided by pi, I would get that the diameter of the nanotube is equal to A divided by pi times the square root of n squared plus m squared plus nm. And so, this is a formula that we can always look up if we need it, but the important thing here is that those numbers, n and m, the chiral indices, that 3,5 or 5,3 nanotube, as well as A, which is a constant, the length of the unit vector, and pi, uniquely determine the diameter of the tube. And we can take this a few steps further. So as you read the Charlier paper, you'll see how we can now derive the chiral angle, which is just the angle at which CH is oriented, because we know A1 and A2 relative to the lattice, and we know CH, then we can just back calculate theta. And we can also define the unit cell of the nanotube, which is the minimum repeating unit. So recall that in the case of the simple cubic lattice, that simple cube is the unit cell. Well, we have a unit cell in the case of the nanotube, and you can see that, for example, as the smallest segment of the nanotube, for which you could copy it 1,000 times and stack them end to end and get the correct nanotube. And that unit cell can be bounded by a rectangle on the hexagonal sheet, and by knowing CH and enforcing a restriction that the translation vector, or the other side here, is perpendicular to CH, you could derive the vector notation for the translation vector, and then you could calculate the area of the unit cell, and then you could then calculate the number of atoms that are included in the unit cell of the nanotube, and then you could find the number of atoms per unit length and so on. So those are all things that I'll leave to you to read about, as well as things that we'll pick up for calculation on the first problem set, which I'll try to get out as soon as possible, won't be due for a few more weeks. And this slide just shows the orientations of the different nanotubes. So here's a zigzag nanotube, here's an armchair nanotube, and here's a chiral nanotube by the definitions we said before. And the chiral nanotube is embodied by being able to see this cool-looking twist of the carbon atoms as you look down the center of the tube. So, and this is this periodic table just put out for organization of the structures, and this may be hard to see, but you have a nice PDF of this on CTools, so take a look at it yourselves. And it also serves as a nice little reference guide for all the formulas that we can use to calculate the unit cells of nanotubes and the numbers of atoms, and so on. So that's where we'll leave things today. I think we may have to move on to let the next class in, but feel free to come up if you have any questions. Thanks.